starting the day off with a bang. So you ready? All right. You're mic'd? A hand for Haym Benaroya.
Hello. It's nice to be here. We're checking the mic. Is mic working? Everybody's okay? All right. Thank you. Thanks for the path up there. Everybody can hear me okay? Reasonably loudly? Okay, great. Okay, so it's great to be here. First of all, I want to thank Andreas for inviting me. We've known each other for many years and met for the first time here, so it's finally great. And thank you for being here on the last day of the conference. I know that that's a tough one after yesterday's long set of talks. So what I want to talk about today is primarily lunar bases, but it's not really just structures. So as we all know that when we have to design structures for the moon, there are a lot of issues beyond structural engineering. And so what I want to do in this talk is give you some background. I'm sure that many of you know a lot of what I'll talk about, but just some background, and then talk about some specific designs, and then talk about how this all might integrate with what we want to do in Starship. So this is sort of this is one of the Icarus models. In fact, we worked on this a number of years ago. And so I guess you can think about this as a prequel, like a Star Wars prequel, right? So this is where we want to end up. How do we get there? So that's really the substance of my talk. These are two drawings by Michelangelo. In fact, they think it's the earliest drawings that he made of the moon. They're not sure that he used a telescope for this. This picture is about 3/4 of an inch in diameter, and that one is about 7 inches. So these are probably some of the earliest sketches of the moon. I thought that would be an interesting way to present. And historically, there are a number of people who were key to getting us into space. And it was really from people across the globe. We have Goddard from the US, Tsiolkovsky from Russia, Esnault-Peltier from France, and Oberth from Germany, all of whom developed rocket technology. And a lot of what we do today really is stuff that they developed. This is from a book by Arthur C. Clarke on space travel. You'll see a lot of art in my presentation. We all used art in our presentations because we haven't built any of these things, so we have to draw them out. Artists work at NASA, and space artists have helped us conceptualize a lot of the things that we need to visualize as we create our designs. And this is a spaceship on the moon. It probably won't look like that, but the essence of the structures that you'll see are like these. Like they're basically shell structures, tin cans or eggshell, because the shell is the strongest structural element, so it withstands stresses most efficiently. This is from a evening Moscow newspaper after Gagarin had his successful flight. And in red, the Russian says, "Soviet man, conqueror of space." So this was the start of the space race in many ways. And so this is the beginning there, back in 1961. And this is a Florida newspaper, Florida Today. It shows a picture off of a black and white TV. In those days, TVs were all black and white, of the lunar surface. And in the bottom, it has Richard Nixon talking to the astronauts, congratulating them, basically saying that this is one of the greatest days in civilization, which in some ways I would agree with. And this is Neil Armstrong, of course, who was not what you might expect to be. His personality was such that other people who would have been the first person on the moon would have had totally different kind of reaction to it. And he basically withdrew rather than extend himself out. He went back and taught college and worked with some companies and really didn't want any of the limelight. He came out a little bit more when he kept seeing the space program continuing to falter. And he made his opinions known when he felt it was right. So this is an interesting video. So this feeds into the people who don't believe we ever were there. Luckily, we now have telescopes that can look at all the stuff left behind on the lunar surface, so we know we were really there, but just in case any of those people are here, which I sort of doubt. So this is a picture of Harrison Schmitt on the last Apollo looking for rocks, and he found one, and so he couldn't bring that one back, so he brought something a lot smaller. Sorry about the podium here, it's probably in your way a little bit. Okay. Apollo brought back almost 400 pounds of rocks, and most of them are still there someplace under Houston space station there, and I think that it's very hard to get those pieces, but they've let out some of the rocks for people who are doing research to identify the properties of regolith, because regolith we are viewing as sort of a prime resource for building structures on the lunar surface. So just to emphasize how I opened up the talk, there are a lot of things that we have to know to be able to build structures on the moon, not just structural engineering. We have to, and I put at the top physiology, psychology, both human and plant. We have to learn how to live on the lunar surface or eventually under the lunar surface. There's a radiation environment, there are temperature cycles, there's dust, a lot of human factors, meteorites, the thermal science and low gravity fluids, power systems, all these things. And obviously there are many purposes for being on the moon. I'll talk about a few of them. People are talking about astronomy, geology, understand where our own origins are on Earth. At the bottom, but not meaning to be last, economic theory eventually has to be paid for, right? Whether the government does it or whether companies do it or whether billionaires do it, somebody's paying for it. And a lot of stuff I'm leaving out here, even from this list, all the electrical issues, electromagnetics, chemical stuff. Everything that we do is like building a whole new civilization on the moon. So it's not really building a structure, you're building a civilization and everything that entails. So the environment, just to summarize this, so I know you probably all know this stuff, but just to summarize it, low gravity. In some ways, that's sort of the most critical issue. It's 1/6 Earth gravity. It affects everything we do. And I think one of the most important thing it affects is our human bodies. We know that a lot of things happen to our human body in anything but 1G. We saw it in microgravity in the space station and on the moon as well. And we don't really know the full extent of the reaction of the human body in adjusting to 1/6G. That's still an open question. We know that if we want to have habitats, we internally pressurize them in some range of pressures. We have to protect against radiation, all kinds of radiation on the moon. There's no atmosphere to protect us there. Micrometeoroids, it's raining these things from little specks to large rocks. And we basically have to hope that the large rocks don't fall where we are because there's almost no shielding against them. And of course, the very large temperature differentials. And people have basically come to the agreement that about 3 meters of regolith cover on a surface structure will shield against almost everything. It won't necessarily shield against very intense solar activity. So we might need special shelters for those, but it'll protect us from almost everything that we need to do. So small meteorites we can deal with, large ones we can't. So if it's this one, we're goners, right? Wherever we are. So we're basically talking about very small ones. So for example, if you take a small fleck of micrometeorite, say like a paint chip, and it's traveling at 10 kilometers a second, that's like a 550-pound object traveling at 55 miles an hour on Earth, a small speck. If you're talking about something that's a few pounds, that's several tons of TNT. So we're talking about huge forces that we can only shield against the smallest ones. So some additional factors. We know from the Apollo era that the dust on the moon is very abrasive. It electrostatically charges, combined with the low gravity, it floats around, it clings to everything, it climbs structures, sort of moves around and just envelops the structures. If you're a human being, then those very fine particles get drawn into your lungs. If you're a machine, it gets into the joints. It pretty much gums up everything and destroys everything in its wake. So very, very difficult problem, but one that has to be solved. Another one is moonquakes. So even though the moon is not seismically active like Earth, we have impacts of meteorites, and we have tidal forces that basically creates seismic effects, and I'll talk a little bit about that as well. So I'll talk more in detail on the moonquakes and the thermal effects a little bit later. So one thing that we always worry about with space is how do we build structures that are reliable over very long periods of time? We really don't know how to do that. For example, if you talk about sending something to Mars, only 50% of the spacecraft that we sent to Mars actually landed on Mars in shape. The rest either crashed or missed it. So basically 1 out of 2. It's not a very good ratio. The Moon we're much better with. Reliability and risk and things like that requires data. One of the problems with the Moon, we have very little data. So we can't go on history in order to create the statistics that allow us to calculate the reliability. That's a big issue. We also want our structures to more or less self-repair because astronauts can't be construction workers. That's the interest in all these other technologies that have the structures build themselves autonomously. And the other thing about redundancies, I won't talk much about that here, but if you make something very redundant, meaning you have all kinds of backup systems to take over, like we have an aircraft and all kinds of Earth machinery, they become orders of magnitude more complicated, and then they become less reliable. So it's sort of a trade-off. So you figure if you make something very redundant, it's more reliable, but it really isn't more reliable. And in fact, it makes reliability calculations more complicated. And then all the other issues that are really are really less known. The physiological issues, low gravity effects on humans, radiation effects. As an example, low gravity affects all the blood flow in your body, and a lot of the pharmacology, a lot of the pills that we take, medicines, depend on a certain blood flow. If your blood isn't flowing like it is in 1G, those pills aren't going to work in 1,6G. So a lot of issues like that have to be solved. And then psychological issues, I'll talk about that as well, and survival of other living organisms. We want to have a lot of plants in particular. In fact, plants are actually more robust in the lunar environment than humans are, so there's a lot to learn from them. I know you can't read this, but this is sort of a framework of all the non-engineering issues, physiological and physical, like radiation, altered circadian rhythms, decreasing exposure in sunlight, psychological, like isolation, confinement, high-risk conditions affects human performance, psychosocial, you have disruption in your family life, you have enforced interpersonal contacts, human factors, you have high and low work levels. We have a lot of experience with Skylab and with other space stations where we saw people buckle under 16-hour days, 7 days a week. And then habitability, limited hygiene, chronic exposure to vibration and noise, lack of privacy, lighting. So there's a lot of issues that we have to work out. Some of them we have ideas about, and some of them we really aren't sure and won't be able to be sure about until we're actually on the lunar surface. So just summarizing some of the key ones about gravity, cardiovascular deconditioning, body fluids shift to the upper body, distortion of vestibular sense, loss of blood volume, cataracts, muscle atrophies, cancer, bone demineralization, 1.5% a month, and pharmacological issues. So these are all things that are very hard to figure out on the Earth because we're full gravity here. We can't replicate the 1/6 gravity. And even though we have data from orbit in the ISS, that's microgravity, which is different. So we have some sense, but it's still approximate. So the Moon is a great resource. This is from the various data sources. You can see 42% oxygen, 21% silicon, magnesium, calcium, iron, aluminum, and other stuff. A lot of these things are very important for setting up an infrastructure, technological infrastructure on the lunar surface. So people have suggested energy production. This is a Japanese sketch. They suggested mining, for example, in this case for platinum. The Japanese company Shimizu, which is a construction company, but they've had an interest in space for a very long time. And this is about 10-year-old concept. They suggested wrapping the center, the equator of the Moon, in a very large set of solar panels. So the whole Moon basically has a belt, a solar panel belt. So a large portion of that belt is always in the sunlight. And what they wanted to do was to basically transmit from that point to various places on Earth where the energy would be converted. So it's a clever idea, and but you can see one thing in the sketch here, continually bombarded with meteorites, so it needs continual maintenance, but interesting idea. Of course, astronomy, that's been sort of the holy grail of the moon as a base for scientific activity. This is a far side base, a concept where it's quiet, it's stable, it's shielded from the Earth's electronic noise, and probably you can see the beginning of the universe at that point. And then tourism. Tourism has been proposed by many people as a way to generate funds. So I read a statistic which is pretty remarkable, that on Earth, 1/7 of the Earth economy is tourism. People who aren't happy where they are and have to go somewhere else, 1/7 of the Earth economy. So it's pretty impressive. So we know that in 1958, Baron Hilton started talking about the moon as a site for a hotel. And this picture here is actually from the early 90s, where Hilton commissioned Peter Inston, who's a well-known London architect. What would a lunar surface structure look like? So here's this one. It probably won't look like that because this is all glass, and we know that we can't put all glass structures on the surface. And the other thing that bothers me is this thing here. It's this huge meteorite just heading right for you, So this tells me that it's not exciting enough to be on the moon. You have to have a meteoroid heading for you to make it really exciting, but that's okay. This is the interior of that Hilton. You can see some exposure area. You can see the Earth up there, and I think that's Coca-Cola, which is pretty disappointing, but that's what it is there. And this is the Lunar Marriott. Oh, sorry, Marriott. I couldn't find a Hilton, but here it is. This is actually the Marriott there. So the structure, again, you'll see that it's a shell structure. It's really something that has to withstand very large stresses due to the internal pressurization. You can see astronauts flying around and all kinds of stuff happening here. And say you were in orbit about the moon and you wanted to go for a swim. And so if you had a swimming pool, we all know that the minimum energy state for water is spherical. So water just goes to a sphere. It's minimum energy. So here are people diving in from all directions. The other thing about this case in zero gravity is that there is no buoyancy. Buoyancy depends on gravity. So if you dive into the swimming pool and you're in the middle there, you're going to stay there, unlike on Earth where you're going to have buoyancy. So you got to realize that next time you go swimming in orbit. So this is now sports on the moon, and we're all of us here would be Olympic athletes on the moon. And the NFL briefed NASA on sports on the moon, and they talk about football, and they said that not only can they run faster, the football players, they can throw farther, but they can pick up their teammate and throw them through the goalpost as well. So that so you can do you can enhance the football experience a little bit. So this is Century 21. This is probably about 10 years old. This is an ad for if you need a new resident subdivision. 240,000 miles from Earth, Big Bang design, world-renowned architect, quick commute on the shuttle, no more shuttle, full and half cradle lots available, inquire at the Cape Canaveral office. So I thought this is from 2002, so that's pretty clever, I thought. I love this picture. So now let's talk a little bit about structural concepts. So we can divide structures into a few categories. So the main categories are rigid structures, inflatable structures, cable structures. More recently, we have to include really 3D printing, layered manufacturing structures. And I put a little quote down here: the longer you do nothing, the more options open up to you. So we've been doing nothing for a long time, and so now we can do layered manufacturing. So I think if we wait another 50 years, who knows what we'll be able to do, as long as we keep doing nothing now. I don't suggest that, but I'm just making a point that we've been doing nothing as far as lunar bases for a long time. Back to some of the psychological issues. As you look at some of these structures, some of the psychological issues are isolation and confinement, which basically lowers your cognitive brain function. You get depressed, you have compulsive behavior. Very heavy workload affects your psychology, and forced togetherness leads to introversion and impairs the immune system. So if you look at the structures, for example, let's start with rigid structures, you'll see that they're all very small. And that's one of the disadvantages. The advantages of rigid structures is that we have a lot of experience with them on Earth. They're very robust, and all-in-one concept is possible. You build the whole structure, you place it on the surface, and you're ready to go. Disadvantages: higher transportation volume, and pressure sealing is considerably difficult. So you look at some of these early studies. These were done during the Apollo era. People thought that we would land on the moon, and of course the next step is to put habitats there and just continue. So that you see they're all circular cylinders, they're horizontal, they're vertical. This is a Boeing study from '63. This is known as the LISA model, I forgot what the acronym stands for. So you have a circular cylinder, you can see here, and then they basically put some regolith on top. They vacuum it up there. Unfortunately, the sides are exposed, and that wouldn't be good. But this is sort of a model for 6 people for 6 months on the moon, and then they would rotate out. Yes?
I'm familiar with that study. That shell on the outside, when they put the regolith on it,
Yep.
filled the sides.
Oh, it did fill the sides over here?
And the upper part was where the people were. And
Okay.
that side's there, but,
Okay. Well, thanks for letting me know. I didn't know that. Okay, thank you. It didn't make sense otherwise that Boeing would do that. Yeah. What he said was that when they fill the top, there's a gap in the wall all the way around this upper portion. So the walls have a space where the regolith fits inside. And actually, I have another one that shows something similar to that. So this is another one where there's a lot of cylinders put together. Like, for example, for a while they're thinking of using space station cylinders as habitats. And they would tie them together and put a framework around them and then cover them with regolith as well. You can see here various images that show various stages of the construction there. And this is another one as well. This might be Mars, but no, maybe it's not Mars. That's not Mars. So here, this is one from Orbital Sciences. It's actually the same idea that you were just referring to. So basically, you fill it from above, and it works its way down in spaces between the walls, inner and outer walls. And again, radiation, micrometeorites. NASA has various concepts where they use electromagnetic devices to deflect some of the radiation. And you can see sandbags here, which is regolith bags really around the structure, basically to shield the structure from all around. So shielding is a critical thing. And then eventually we hope to go to a second, third generation using more local materials. When this drawing was made, there was no layered manufacturing yet. But eventually that would be the case as well. So the concepts develop and we build an infrastructure slowly. Eventually the hope is to put them underground, which is a big deal. Cable structures, just to show you one of them, this is a clever idea by Eichhold, and she thought if you could take a crater and clean it up a little bit in a sense, and hang cables all around, cover it, and then pressurize it, you have a very large volume. So it's a very clever idea. And inflatables, which I think probably, short of layered manufacturing, is probably the most suitable for lunar surface structures. It's a very low mass of the main structure, deploys fast, simple foundations. I'll show you some pictures. If the volume is very large, you'll need an internal structure because it's a big volume. The robustness is difficult. There are challenges with inflatable structures and a small experience base, although that's increasing as more and more are used on Earth. So this is early ones. This is from the 90s. Again, each of these is an inflatable structure. We see it being covered up here. A more elaborate one drawn by Gary Kittmacher, who, by the way, is an engineer, and I was very impressed to find out that an engineer can draw this well. So this is an inflatable structure, not to go to stereotypes, but you can see six levels here. You can see plants, and the habitat is underground. The ground level is somewhere on here. So they sleep down here. And you can see, just it's an interesting one, you can see these astronauts, this one is jogging. You can see the floor has to be inclined almost, where he's jogging, almost parallel to the floor because of low gravity. Otherwise, he would fly off when he runs, or she. So this is a sketch of it. You can see various levels. This is another one, also from the 90s, from T.Y. Lin, which is a structural engineering firm. And this is an inflatable structure again. And you can see the process. You lay it out, roll it out on the surface, which has been smoothed out. The outer toroidal structure will be inflated, and then the complete thing is inflated, and then it's made rigid. There are gaps between the walls where you can put something in there to make it rigid, and a lot of that technology is actually developing quite well. And you can see they filed a patent because they thought this is a really great idea, and it actually is a great idea. And then there are other inflatable concepts with a core in the middle, and this one is holding regolith all around, and a solid one in there. We know TransHab, which is that kind of concept, and now is out. One of them is at the ISS. TransHab survives. It's an inflatable structure of many, many layers of different materials for different purposes. Some for shielding from temperature, some from micrometeorites, some for holding the thing together. It's also a great idea. And this is Carter Emmert, who's at the New York Metropolitan Museum of Natural History. And he developed these concepts. I think these are Mars. I know Mars and Moon are also a big debate. So Moon is definitely the only way to go. Mars is a later way to go. I know people don't like that. So Mars takes 9 months about, the Moon 3 days. You have 40% of the sunlight on Mars compared to the Moon. Double the gravity. As I mentioned before, we just can't get to Mars. We can't guarantee that we send a spacecraft to Mars, it'll land, it'll be reliable for that long period of time. We just don't know how to do it. Just a fact. You see the greenhouses in the back there. Here's the interior of the greenhouse. Astronaut on the outside. Plants are a big deal. I don't have time to talk about that here, but plants are remarkable in their suitability, and actually you can put plants in regolith with certain bacteria, and they will grow. It's pretty remarkable. Another advanced concept. So, the visions are really great, and I love these more advanced visions as well. The problem is that they depend on a lot of stuff happening beforehand. This is a crater that's now being layered with solar panels. And ISRU, in situ resource utilization, very important. We want to be able to use local materials as much as possible because it's so expensive to bring it from Earth. So you end up with things like sulfur-based concrete, waterless concrete. A student and I did a study where we were able to take regolith and just basically sieve it so we get certain grain size distribution, microwave it, and you have building blocks that's stronger than concrete. So there's a lot of stuff there that can be used for building and other things. Deployable structures are very important. Again, small size becomes big size afterwards. And rover bases have been suggested. These are pressurized rovers. Advantage is that you can move around to other places. And this is called Haybot, a habitable robot from NASA concept where they look for rocks, and they can be put together into a habitat. So you can basically rover, go throughout the moon and find places where you have places that you can do things that are important to you. More recently, lava tubes have become more and more important in the sense that we always speculated that they existed on the moon, but very recently, from the Selene images from about a decade ago, they started actually seeing pictures of them. This is really a remarkable one. This is Tranquillitatis, Mare Tranquillitatis. So this is 100 meters across, 300 feet. It's about 150 feet deep. On some of these lava tubes, they think that they actually, at the bottom, there are tunnels that emanate from them. So, you basically have a place where you can go down into, and you have a lot of shielding all at once. So it's just like artistic rendering of what that might be if you don't pressurize it. Ideally, you'd like to not have to use pressure vessels inside them. You'd like to be able to seal the lava tube, so basically you have a large volume again. The Russians have talked about this as well. You can see a huge lava tube facility. You can read the translation here. It's a whole city underground. And the Russians have a lot of very elaborate concepts. They were 2050. These are about 20 years old, so a little bit out of date in a sense. Again, very large facilities, so I would say this will happen, but I don't think anybody here will see that. I'm sorry to say it. Here's a case where a whole area has been excavated, and then the structure built, and everything was covered up. So it's pretty elaborate. We don't know how to do that yet. So I'd like to spend the next segment just talking about some of the studies that we did. So this is a little bit more technical. So some parts I'll go a little bit quicker. Anything that anybody's interested in, if you email me, all this stuff has been published. I can send you the papers. I'm glad to do that. Just email me. So we started doing some analysis. We wanted to see whether we can actually analyze the structure for the moon in a feasible way, very large factor of safety, and yet still being feasible. So we started, and we thought about a very simple structure like an igloo structure. In this case, you basically have two arches connected at the top, held together by a base, and then pressurized on the inside. So it's a very strong structure. It's about 5 meters tall, and we applied factor of safety of 5, and we're able to go through a design accounting for the internal pressurization, the regolith cover for shielding, and then we had to design the actual beams, the arches themselves. So we looked at the different cross sections, and we came to a double I-beam. initially at that stage, we used aluminum. We won't use it, later on went to magnesium because there's a lot of magnesium on the moon, and if you can shield it properly from oxygen, then you have a good structural material. And so you have this igloo, and you have end plates. So we analyzed the stresses on the end plates, and then the tie floor. So those are the main components. So the tie floor is not uniform because the bending moment at the bottom is not uniform, so we want to save material by shaping it to the bending moment. And then the connection. Whenever you internally pressurize a structure, what's your first concern? Well, the first concern is that you're going to lose oxygen. And so the connections are really important, and one of our co-researchers came up with this idea where this two parts mate, and you have a very large surface area here, reducing the loss of oxygen. And this is at the base, similar idea. And then there's welds. So this is I'm just showing you this because it's an actual design. There are welds, there are special tape that we put on seams, all to basically keep the pressure contained. And then you have to construct it. So you put the tie at the bottom, temporary scaffolding, the first arch, then you put the second arch, then you weld where you need to, you just seal where you need to, and then you have your structure. And the nice thing about the igloo is that you can configure it in a whole bunch of different ways. Depending on what you want to do, you can expand it as well. And this is what it might look like with an artist rendering. Our structure didn't have a door, but a door is a good idea. So here's a door there. Just thinking after the fact, the door is good. And so that was our first try at a design. And more recently, what we did is we took that structure and then we switched to aluminum, and we then looked at thermal effects as well as micrometeorite effects. I won't go through the details, but the thing is, at the equator, you have temperatures from about 100 plus to minus 153 degrees Celsius. At the polar regions, you have minus 113 to minus 153, a little bit smaller range. I know that the South Pole is really being talked about as the place to go for various reasons, but the South Pole is very, very hilly, very rocky. The sun is almost at the horizon the whole time. Makes it very difficult to operate. So I think there are real challenges for the South Pole. We like the South Pole because of the water, but people have said that there's water elsewhere as well. I won't really go into that, but so we have our structure again. At this stage, we added the doors. We wanted to see what the design was for the thickness. Again, internal pressurization. As a structural engineer, you always worry about corners, because corners, you have stress concentrations. So whereas the whole structure might be great as far as the stresses, you might have double or triple stresses at the corner. So that's what this is talking about when you have imperfections. So that becomes part of the design as well. So again, we did factor of safety of 5, internal pressurization 1 atmosphere. So we did a CAD model, and we looked at factors of safety. This is a graph that shows you the temperature change. So you have the daytime, and then you have nighttime. And this equation basically tells you what the temperature will be depending on where you are, latitude, and the sun's angle. So based on that, we're able to figure out this equation. This tells us the heat per unit area that radiates from the sandbags into space, heat per unit area interchange between the sandbags and lunar surface, and then the solar radiation heat absorbed by the sandbags, which then goes into the structure. So we need to figure out the heat flow. And the reason we care about the heat flow is because you have to design the mechanical components in the structure to make the temperature inside the structure pretty constant for the astronauts and for the machinery. So there are things called configuration factors, which tell you how the incidence of the sunlight rays impact the structure and how they bounce off. That feeds into that equation. And so this is one example. So we see that this is the sunlight over here coming from this side. On the other side, it's dark, so temperatures are much lower. So we can see this is 120 K, which is about minus 153 degrees Celsius. Over here, you have 343 K, which is about 70 degrees Celsius. So different parts of the structure or the regolith on top are at very different temperatures. And we know that we have to worry about temperature differentials. They can create stresses in the structure. So we worry about that a little bit. And this is at nighttime. So basically everything now is the same temperature. And these are really nice. So you can see this is a cross-section of the structure. Here's the hot part. Here's the cold part. And this shows heat flow. So heat is flowing in from this side because that's where the sunlight is, and flowing out where it's dark. And this is at nighttime. We see heat flowing from the inside out in all directions because now the outside is much colder. So these kind of studies allow us to understand both from a structural point of view and from the mechanical point of view what to do and how to design these things. Second part we'll talk about is lunar seismicity. And a lot of this information is from a network of 4 seismometers that were left by the Apollo missions. And they got a lot of data. There's also a lot of uncertainty about the data. And generally, it's not a huge problem, but if the structure is very flexible, like say maybe like a telescope or a disk or something that's not habitat, it might vibrate a lot from seismic activity. And the difference with lunar seismic and Earth seismic is on the Earth, a long earthquake is about 2 minutes long. On the Moon, a long earthquake could last 10, 20 minutes. So this thing is vibrating a lot for a very long period of time. And we worry about things like fatigue of the structure. So there's different kinds of moonquakes: deep, thermal, meteorite, and shallow. The shallow ones are the ones that we're concerned about. And from the Apollo information, there were over 1,700 events. And the largest mass was approximately 2,000 kilograms, going at 22.5 meters per second. Magnitude, Richter magnitude was in the 5 were the maximum ones. And so most are a magnitude or 2 lower than that. So we were curious to really understand, is this important for a structural design? So there's a lot of information about it. And what we did is we looked at some of the seismograms. And then we created an energy curve. So this is a spectral density. A spectral density basically is a function that tells us the energy distribution within the earthquake at different frequencies. And we see it changes in time. And with this, we can figure out how the structure responds, how it deflects, how it shapes. So this is we picked one of the ground motion accelerations. We loaded the structure. And then we had this is sort of a evolution of the dynamics of it. We have the frequencies. The frequencies are important because there's a concept known as resonance. And sometimes if you have 2 different components that are oscillating at the same frequency, they can reinforce each other, leading to very large amplitude motion and failure. So we care about those things. And this is sort of looking at the stresses, static stresses, vibration stresses. And then we looked at some results. We saw that most of the structure was okay. We did see, however, remember I mentioned the stress concentrations. We saw in this region where this leads to the doors, the entrance, there are high stresses in this region. So in order to optimize the structure, you would make, for example, here where there are not high stresses thinner, and you make the region where there are high stresses thicker. So those kind of refinements can be made using the analysis. So construction is very difficult. 3D printing would be great if we can go there and we can actually do what this image shows, basically have automated systems using regolith, processing it, and creating igloo-type structures, and have these things happen a year before astronauts get there. In fact, we can do 3D printing with multiple different materials, so you can actually build in the electrical systems in the structures, you can put pipes, you can do everything in there. So we know we can do 3D printing with very complex materials, very complex geometries. So this is for Mars, but you can see send robots, just start building it. So this is just a conceptualization. That's sort of the ideal situation that would make things a lot quicker. So Frank had it right. So you want to get to the moon. So Jules Verne, I think Jules Verne was talked about yesterday sometime. So I think that's enough, Frank. Enough. So what's next? So there's a talk this afternoon on the space elevator, which should be very interesting. Space elevator, as probably all of you know, is basically, the idea is a very long cable, roughly 60,000 miles, orbiting around the Earth. Counter mass and geosynchronous orbit is the center of mass. It orbits. It allows you to have climbers that move up and down. It basically allows you to bring stuff into orbit, either low Earth orbit, geosynchronous, or have it run off the end and go into orbit and go somewhere else. Really cheap access. Carbon nanotubes, which you can see here, are really what allowed the concept to go beyond fantasy into possible reality. There's still many issues that go into space elevators. But I think they are a future. And as somebody mentioned in one of the talks yesterday, we really can design space elevators for orbiting the moon. They're a lot simpler than orbiting the Earth. So let me show you this really cool video. This is the real one this time. So Alan Chan is actually a Hollywood animator. And about 10, 15 years ago, when Brad Edwards came out with the space elevator idea, he got really motivated and he decided to see what it would look like. So he created this animation. So you'll see the ribbon come up. So the ribbons are very flat, very thin carbon nanotubes that are woven. In this concept, they use lasers from the ground to shoot at the base of the elevator climber, giving it energy to go into space. There are other concepts. And here you'll see many different kinds of climbers for different purposes. So there are 100 challenges to this, so I'm just putting it out for you. So the idea is you have a lot of these elevators, and you have them around every planetary body, and then you can go ahead and basically go between planets this way. So I think it's a pretty cool video. It's pretty motivational, I think, and I think some of that may come forward. Oops, sorry. So now bringing it back to this conference a little bit. A couple of years ago, one of my students, Sri Reddy, did a master's thesis on the analysis of the reaction chamber of the Icarus spacecraft. So this is the spacecraft here, and in here there's a container that injects pellets into the reaction chamber, and they explode at a certain frequency, and as they explode, they provide impulse to the structure, which then can be accelerated over long periods of time to high speeds. And so part of the design of such a structure, just like some of the earlier structures that were very simple by comparison, is to figure out the stresses and make sure that everything is what it should be. So here's that segment again. Propellant storage, there's the pellet, and there's the ignition. And then this shell structure here has to be able to absorb that explosion. It's a nuclear explosion. It has to absorb that explosion and all the radiation and all that and survive for thousands and thousands of explosions. And so the material is molybdenum. There's only a couple of metals that can take the temperatures. Molybdenum is one of them. I think the other one is tungsten. Maybe there are other newer materials as well. And so what he did in his analysis is create a model of that structure. And so the way that we analyze very complicated structures is we break them up into small pieces, like small triangles and pyramids in 3 dimensions. And then we solve each of those separately, and then we put it all together to get the response. This structure is so large, it has 100,000 pieces. It's broken up into 100,000 pieces. And then this shows you the stresses, and we can see very large stresses around this. Now, in the actual structure, it's a very small hole there for this feeding. We found that we couldn't make it survive because the hole is so small because of the stress concentrations, it would always fail. So we made the hole larger, you can see, so it would survive. So we made it large enough so that it would survive even though there are very large stresses around the end. This is the spacecraft just for scale. I thought you'd like to see what it looks like. Probably the model has evolved over the past few years. And just acknowledging my students, so the early studies on the designs, Florian Ruiz, Srikanth Reddy for the Icarus, and Saurabh Mutagdi for the more later designs as well. So thank you. Hope you had a good time. And we made it in time. You should, right? How's that?
What are you, some sort of anarchist?
So I think we have time for a question or two.
Questions?
The seismic data.
Yes, how long was the space elevator from Earth? The one that was,
The ribbon was 60,000 miles.
okay, what about transiting the Van Allen radiation belt?
Radiation is an issue, right?
Yeah.
So it has to be designed. There are a lot of issues. You're right. So there's issues from the first couple hundred miles, the turbulent forces from the atmosphere, all kinds of issues, definitely.
The number of seismic events that was reported, over what period of time was that?
I think about 15 years.
Oh, okay.
They lasted over quite a bit of time, but they're all where the Apollos landed only, right?
Hi, Haym.
Hi.
Thank you. That was such an exciting presentation.
Thanks.
I've got a construction question.
Yeah,
The lunar regolith and the dust is incredibly abrasive.
that's right.
And it actually got through all of the airtight sills
That's
of
right.
the moon rocks that were being brought back to Earth.
That's right.
So are there any ideas, any studies on how you can prevent the damage to your structures?
Right, so the short answer is it's an unresolved question. Some ideas are, since the regolith is charged, people are thinking creating, first one is to vacuum, keep an area open and one idea is to sinter the regolith a certain distance from any structure, so there's nothing loose in that area. Another is, I think I had one slide showing electrostatic shielding that would basically repel the regolith as well. So those are some ideas. And the abrasion is a big issue. It's also unresolved. So the regolith is one of the key problems, both for human survival and for machine survival. But those are some of the ideas, and people are working on that. I would say it's unresolved. There just are some ideas out there.
I was interested to know why you chose to put a full atmosphere in the structure that's going to be in the initial missions.
Right. So there is a range that people say is acceptable, anywhere from 10 to 15 pounds per square inch, more or less. I think we wanted to design it as conservative as possible, so we did the maximum. And the internal pressure is the design load. It's the maximum load. Even with regolith on top, the internal pressure is the key loading on the structure. So we wanted to make it the maximum case. Although you're right, some may put in only 10 psi. So that becomes more of a physiological issue, design criteria.
Hey, Haym, thanks for your talk. You mentioned using lava tubes on the moon. If they were pressurized, would their bare walls be sufficient to hold the gases that you put in, or would they need to be reinforced with some additional materials?
Right, so the current information on lava tubes is that they are very dense. And the main concern is that if the lava tube area is hit by micrometeorite, that it might actually cause damage. Even if it doesn't go all the way through, it might create stress waves, and it might spall on the inside. So that would be one issue, depending on the configuration of the lava tube. So some suggestions are to basically seal it with some material that's impervious for the purpose of retaining the gases that are inside. So it's structural issues and the one that you mentioned with the losing the oxygen or the gases.
I had a question for the structure where you actually had thermal differences.
Yes.
You guys look at maybe putting ammonia through or some type of liquid to make sure that you essentially don't end up getting any thermal stresses by making the temperature uniform throughout the external or throughout the structure?
Right, we didn't look into that really. So what we did was basically just to figure out what the stresses were rather than to solve the problems. Some people have thought about actually putting piles into the ground and using that maybe with heat pipes to draw the thermal energy out of the structure as well.
The other one was also the same thing with the earthquakes. You're having dampeners underneath the actual structure, so
Right.
that way you don't even have to worry about that.
That's right. Yeah, so you're absolutely right. So I think first we wanted to see whether there was a real issue to worry about. And probably for the case that you were saying, probably under equipment like telescopes and things like that, which are more susceptible to the damage, you would do something like that.
Then the last question, the stresses for the tension in the space elevator, from what I had read, it's like you need materials that are like order of magnitude stronger than diamonds. Has that changed, or?
Right, so the carbon nanotubes are much stronger than the diamonds. So in principle, the carbon nanotubes are the only material for an Earth space elevator to withstand those stresses.
So in tension, it could actually handle the tension?
That's right. In
carbon
principle,
nanotubes?
that's right.
Okay. All right, thanks.
Haym, talk timelines for a minute. So reality, where we are today in 2017, assuming we really were going to the moon via the government or the ESA Lunar Village or something, or the private sector, what's the soonest, given our TRLs, that we had to have an operational lunar base?
I would say really the soonest, maybe 10 years, 15 years. If we started and really took it seriously, we can probably place a cylinder on the moon, we can shield it, and we can basically put people there.
So a decade or a decade and a half?
I would say, I don't see doing it any quicker than that.
I don't like that answer.
Is that too soon or too late?
One more question. Thanks, Richard.
It was an amazing presentation. Thank you very much for that. And I
Thanks.
would like to ask, where do you think would be the best, if you had to choose the perfect spot for this lunar project, where would you choose this place to be?
Right, so there are a lot of constraints on that decision, so that you have to balance off, and water is obviously an important thing. I think if they can find water else other than the South Pole, I would avoid the South Pole. The South Pole seems to be very problematic from a number of reasons. I don't have a specific answer for that. I think that it really depends on if we can find water elsewhere, like there's some signs that there are water elsewhere, then I would prefer those places.
Many years ago, I read about lunar transient phenomena.
Lunar what?
Lunar transient phenomena.
Okay.
Years. Some of the speculation was that it was water vapor. Let's see, crater Alphonse.
1 second, people.
Years ago, I heard about lunar transient phenomena that had been observed from the Earth that appeared to be water vapor. If memory serves, it was Alphonse crater. Mm-hmm. Do you know anything more about that? Is there any current or new data on that?
I'm not familiar with any new data.
Okay.
I have another question for you, Haym. Science fiction has popularized the idea of mining helium-3 on the moon for fusion fuel, but I've read papers suggesting that that's not really a very effective proposition, that the density of helium-3 on there wouldn't make mining realistic or efficient. Can you comment on that?
Right, it has been popularized a lot, and it presumes the existence of nuclear fusion reactors, which, I don't know, the physicists in the audience can say are maybe several decades out, I believe. And I've read a recent paper that also confirms what you just said, that it's really not that great a source for helium-3. But that would not be the reason to go to the moon, I think. It doesn't really make the case, at least not initially.
All right, I think that's, oh, one more? Certainly.
Just a comment, and whoever told me this yesterday should pipe up. Apparently, there's quite a market for helium-3 right now. It's used in neutron detectors, and
Okay.
the prices are on the order of $1 million an ounce. There's none being produced.
Oh,
So
really?
you might not need to wait for a fusion reactor.
Okay. That's a good thing to know.
Okay.
All right,
And
thank you
and
very
with that,
much.
thank you. Haym Benaroya.
Thank you.